So continuing on the theme of nuclear clocks, our next speaker is Thorsten Schumm.
Yeah, thanks. Good morning. Thanks for having me. It's a very impressive building also. We're currently building a new physics faculty in Vienna. We're planning to do that. Is the microphone working? Maybe it's working, but I'm not speaking into it. Maybe I should move it up. Is that helping? Otherwise, I can just try to hold it. I just raise it. Is that okay? Can you? Okay, let's speak it up. Good. So yeah, thanks for having me. I'm getting a lot of inspiration how our new physics building could look like by walking around here and enjoying the catering and stuff. I come from Vienna. My institute has a very old-fashioned name. It's called the ITAMP Institute. You wouldn't name an institute like that today anymore. But it kind of indicates it's where it comes from. And we have a small nuclear research reactor. So we have a nuclear physics part in our building that has been complemented by a whole lot of quantum physics in the last 10, 15 years. So it's an interesting mix between, topics that usually don't speak to each other or have a lot of overlap. So I'm happy to speak about optical Mössbauer spectroscopy here, which is a little bit like making a bridge between these two worlds. All right, let's see if that works. It does not. That's just one click away, I think. No, here we go. Okay, great. So if you have questions, just interrupt me anytime and ask, or write them down and send me a mail later. I will have about 3 parts. I will quickly pick up on this topic of building crystals. And very quickly run you, after June has done this brilliantly, I can be very quick on like summing up the history of what's been done in the nuclear transition in terms of crystal achievements or effects. I'll speak a little bit more about something that you also already have heard a little bit, but focusing on the material science aspect of VOV cone spectroscopy that has been performed and what we can learn about the materials. So as I already kind of joked up, I brought a little crystal here. So this is how they look like. This is a thorium-containing calcium fluoride crystal, but don't be alarmed. This is the wrong isotope. So this is the thorium-232 isotope that is stable as far as we know, and we use this as a dummy, as a proxy to do many of the optimizations to not like lose the precious 229 isotope, which is very rare. There's just a few milligrams of this material on this planet, so we have to be really sure of what we do, and we practice with this one. And then, so the aim here is to say that there is an intense interplay between the nuclear degrees of freedom and the surrounding material electronic degrees of freedom. And I will give you in the third part of the presentation a few indications of where we already see a coupling of nuclear and electronic degrees of freedom. And to some extent, I think this will fulfill June's wish of finding a way to quickly get rid of the nuclear excitation once it's been read out, to restart an interrogation cycle in a clock sequence. We call this quenching. Okay, so here's the basic concept. When we started this 15 years ago, the idea was we want to freeze as many as thorium nuclei into some material to just be able to, like this, carry it around. And that's exactly what we do at the moment, perform a lot of experiments in different laser sources, synchrotrons, other places around the world. So this is essentially our ion trap to some extent with a very, very high density. And we thought, like, okay, we have to find a way to put the thorium into a material. There are many ways to get material into other materials. But one of the main things is that the material needs to be transparent so that we can actually reach the nucleus with electromagnetic radiation. And it was said that if the band gap of the material is large enough so that it is larger than the nuclear excitation energy, these two will essentially not see each other. The nucleus has no way of getting rid of its energy, which is called a process called internal conversion. And so these two will essentially not see each other, and we really have frozen nuclei with a high density that we can carry around if we want to. So that was the idea, and you've seen these pictures in June's talk. The idea is we take an ensemble, we get a high density. They were main names already, so we have about 10 to the well, this is rapidly moving flesh here. We have about 10 to the 15 nuclei per cubic millimeter. Atom trappers and ion trappers will scratch their heads if they see these densities because of interaction effects. For us, this is still very dilute, so that means we replace only a few of the atoms in the crystal by an impurity atom, in this case thorium. So that for us, this is still very dilute. We can still increase the density by some orders of magnitude, and that's hopefully what we're going to do when we go to other materials. But the idea was, again, the separation between the nuclear degrees of freedom and the environment. The environment was initially just supposed to hold the nuclei in place and otherwise do not interfere. And then we could do nuclear clock interrogation. We would find the true, like, inert, real thorium transition. And the purpose of this presentation is obvious, to show you that it's not as simple. There are interactions between the environment and the nucleus. And they are interesting, and they teach us something about fundamental physics and nuclear properties, but also about material properties, and that's the Mössbauer aspect of this presentation. All right, so very, very quick run through, and this has been mentioned already. Before we had laser excitation, the way we learned about properties of the thorium nucleus was through nuclear decay channels. That meant we found ways that parent nuclei decayed into thorium, and while they did, they populated the excited states of the thorium nucleus, among them the low energy H9 UV state. And there are several decay processes. Some are alpha decay, uranium alpha decays into thorium-229, actinium beta decays into thorium-229, and so on. So these was the way to populate a nuclear state, was a very, very brutal nuclear decay process. Okay, so very far away from the fine, precise quantum manipulations you're used to. This is really nuclear physics at its best. Okay, so and the killer, like, changing experiment was performed about 2 years ago, 2.5 years ago at CERN, where the group of Piet van Doepen from Leuven University operates the Isolde or uses the Isolde beamline facility at CERN, where they produce a beam of actinium-229. Actinium-229 is here in the periodic chart, and it beta decays into thorium-229 and populates the excited states. Okay, so the experiment was stunningly simple. You take an ion beam. Where is my okay? You take an ion beam. You implant these actinium nuclei in a beam with a high energy 30 keV implantation. You shove them into a transparent material. Then there was a mechanical motion. So there, after half an hour of implantation on this wheel, these samples were moved over here in front of a grating spectrometer, and people were just gathering the photons that came out. And I would have bet, and I did bet, a lot of alcohol too, so that never worked. And I was drinking even more alcohol when it worked, because all of a sudden, yes, indeed, actually, they saw a photon coming out of these crystals, which were implanted. So this is really a very brutal way of putting material into other materials, just high energy implantation. So very dirty chemical environment, but still the photon came out, and that allowed us to kind of pin down the nuclear excitation energy that we would need to excite from the ground state to the first excited state.
First thing you went to ask.
Sure.
So here, the reason you can see the radiated photon is because you've frozen the internal conversion because it's a highly converted transition, right? So this is a photon that you see.
This is a photon that I see.
And so the electrons themselves are in the higher orbit are not converted because they're frozen in this lattice.
Well, so the photons that I see, they come from nuclei which sit in a lattice position where there is no electron wave function overlap with the nucleus in an energy range that makes internal conversion possible.
Okay.
So these are the few lucky ones.
Yeah,
I'm sure there's thousands of other nuclei which sit in another environment where they give their energy to the electron and they decay through some other channel. So this is not every boron thorium excited state is emitting this photon. I think it's about 1%.
Yeah, and so you see this as an effectively longer half-life of the.
No. These ones are the good ones, and they decay almost unperturbed. The other ones, they are gone immediately. So there's essentially two groups of them, depending on where they sit in the lattice. At least that's the basic image we currently have. But June with his thorium fluoride is somewhere in between. So I'm kind of torn to interpret this one. This is complicated. But I'll come to that in the presentation. These were actually two different types of material. This is calcium fluoride and magnesium fluoride, standard materials in UV optics. It's the ones that are transparent in this kind of wavelength. Okay, and from this they concluded the isomer energy and also the lifetime. And the lifetime, as it was said already, is 10 minutes order. Okay, 10 minutes of an excited quantum state to fall down through spontaneous photon emission. That's quite a long lifetime. Good. Okay. So we've seen that one. But this is, we call this, when I go back, I think I've even written it somewhere. It's up there. We call this population through stochastic decay. So that means we need to wait for a nuclear decay event for the isomer thorium to be born stochastically, and then it comes down at some moment with some lifetime. But there's no control. So the next step was, how do we gain control? We gained control in an experiment that we were performing at the Spring 8 synchrotron facility, where we excited to the second excited state using 29 keV X-ray radiation. So we essentially pump up nuclei to the second excited state. That's actually what nuclear physicists are much more familiar, is to go to these high energies, to these high energies, and then this one spontaneously goes down very quickly. This one has an 8 picosecond lifetime. And then this one goes down here, and this one lives for 10 minutes and emits the UV photon signal. Okay, so this can also be detected. And here we go. So we have a decay, and we confirmed that about 10 minutes lifetime. And then people, the Japanese were before the photomultiplier, they put a set of filter wheels, and by changing the filter wheels, they were able to determine also the wavelength, and that fits quite nicely to the energy that was predicted in the CERN experiment. Okay, so these two experiments, they all go through higher states. So they don't start in the ground state and go to the first excited state. This was done quickly after in the two experiments that were mentioned. One performed at PTB in Germany and one performed at UCLA. Essentially, conceptually, almost identical, both using crystals, different host materials. So this one is calcium fluoride, so very much like this one here. This is our crystal. UCLA uses a more complex material, which is called Listings tungsten aluminum fluoride, another classic in VUV optics. But otherwise, it's the same thing. And to our great relief, we find very similar energies and very similar lifetimes, which is part of giving us the right to claim that this is a nuclear transition, because it seems to be independent of the material, and hence it is not some obscure electronic state that happens to be narrow line-lived and long-lived, because we find it in two very different materials. Great, this was published, and so this is my little history. This covers the last 2 years. Okay, so this is a very recent history, all of this. Okay, so from this perspective, it seems like everything is working, and Jim has shown a similar graph. We are narrowing down the energy, and so far it looks like the concept of, okay, I have this nuclear two-level system sitting nicely in some material seems to work, because everything's kind of coincides. If you look closely at the lifetimes that I have shown, there was some variations, but the variations that come essentially from material parameters, because spontaneous radiative decay of whatever quantum two-level system has a lifetime which is scaling with the refractive index of the surrounding medium. And as I said, we have a decay within a surrounding medium. So that means the refractive index enters the decay lifetime. So if we compare experiments performed in vacuum and experiments performed in material, there is an n to the power 3 scaling, n being the refractive index. The refractive index is quite high, so there's actually a factor of 4 acceleration of spontaneous decay in these materials compared to free space. Okay, so that means that the isomer lives for 40 seconds in free space. So it's even worse for in Wuj's perspective. Okay, but all of that kind of seems to match up and nice. Okay, so now comes the experiment that was performed at Gila, where we deeply go into the substructure of these transitions. So this you've already seen. There were individual lines that were observed. I don't have to say a lot of this, apart from how fantastic it actually is that it works. So I wouldn't have that. Anyway, so these are the 4 or 5 lines that have been determined in absolute frequency determination, and they allowed us to reconstruct the nuclear structure within the material, and I'm going to say a few words about this in a few slides. Good, and this is the point where I thought I should mention the work of Mössbauer and the whole field of Mössbauer spectroscopy, but Jim has already done that. So in the past, these kinds of structures were indeed already investigated in gamma spectroscopy by using gamma emitters at very, very high energy. The sources were, again, spontaneous stochastic decay sources. So one had some kind of nuclear decay leading to the emission of the gamma, and the absorption of this gamma was then measured by a detector. And in order to detune the emitter and the detector, the material that was detecting to actually have spectroscopic resolution, there was the mechanical motion of the sample. These were usually glued on a loudspeaker membrane, which was wiggled back and forth, and through Doppler effect, you had a resolution in space, in frequency space. So this is why in Mössbauer spectroscopy, you always have this infamous x-axis, which is in velocity curves. Oh, yeah. Anyways, but the experiment that June presented this morning is replacing this part by a tunable laser. So the sample doesn't have to move anymore, and we don't need these units. We can put units we're familiar with, like hertz, kilohertz, or electron volts. That's whatever you. So this is the link to Mössbauer spectroscopy, but again, it allows us to spectroscopically resolve a nuclear substructure that develops under the influence of an outside material. So it's not a two-level system anymore. There is a back action of the fields that are surrounding the nuclei, including the fields generated by the own electron shell of the thorium, that leads to the emergence of level splittings and a more complex level structure than just the 2 levels. And that's the point. Just to give you an order of scales here, these are the spectroscopy scans that have been, this is the PTB data, but the UCLA data, if I put it on here, will look exactly the same. So this is a nice Lorentzian excitation spectrum. That has been measured with a few tens of, about 10 gigahertz resolution. And if I put these 4 or 5 lines in here, I actually don't manage because the resolution is so small. So that means we're kind of zooming in on this on this spectroscopy features in order to be able to determine the nuclear substructure. And the paper has been shown also already in June's talk. Okay, so. This you've seen also, so yes, I can really go very quickly through this talk. Maybe I actually add a few slides at the end. Let's see. But it's interesting. So that the level splittings that emerge here. Once I get this thing, yeah, Pete said that this takes getting this to, and he's right. So these level splittings here, there's currently 3 level splittings here, which are arranged in a clever way, or by coincidence, and it took me a long time to really understand that this is true. There's a sum rule that you can apply that always kind of leads to this unperturbed free transition energy here. But there's these 3 separations here, and they're dominated by one nuclear property, which is the spatial anisotropy of the nucleus. The nucleus is not a ball, it's more a football. I'm in the US, okay, it's a football. So it's a prolate object. And that means that because of the protons are to some, we assume the protons to be evenly distributed within the volume. That means a prolate form gives rise to an electric quadrupole field. This electric quadrupole field interacts with an electric field gradient, if there is any, and there is an electric field gradient, obviously, because otherwise we wouldn't observe splittings within the material. And this electric field gradient, so there's the quadrupole moment, that's a nuclear property, and that doesn't depend on the material. But then there is the electric field gradient, which is characterized by 2 quantities. One is the gradient, and one is the anisotropy parameter, which essentially tells us something about the topology of the electric field that the nucleus sees and how deformed it is to some extent from a classic quadrupole distribution. So these are material parameters, and they obviously strongly depend on the material. And they even depend on temperature, as we have seen, and we will see again in a few minutes. So that means we can extract on the one side nuclear parameters, on the other side material parameters that depend on if you put it into calcium fluoride, magnesium fluoride, function with aluminum fluoride, or I don't know, glass, whatever your preferred material is, unless it has to remain UV transparent. Okay, good. So the change in quadrupole moment when the nucleus goes from the ground state to the excited state, the spatial anisotropy changes a tiny little bit. And that is very interesting from nuclear physics perspective, because that was a missing number in order to determine the sensitivity of this nuclear energy transition to variations of the fine structure constant. So this is very interesting for nuclear physics. So we have now means to probe nuclear physics properties through laser spectroscopy, which is amazing, I think. But also we can learn something about the material, which is maybe less exciting, but also very relevant if we ever want to really use this for our clocks. So this is why this talk is going to be more on these 2 other parameters. All right, good. And these parameters, as was already mentioned by June, they change even in the same material. They change if we change the temperature. If we change the temperature, obviously there's thermal expansion. That means the electric field gradient changes a little bit. The electron density at the position of the nucleus changes a little bit, and so on. So that means we have to get away from this image of the nuclear 2-level system being decoupled from the material, because on the fine and fine structure is a term maybe I shouldn't use, but on the finely resolved spectroscopic level, there is a coupling between the material and the nucleus. All right, good. Yeah, that was submitted. You'll see that. So now, just a few words on how we build these crystals, because now we will have to speak about a specific host material. And the one we currently use most of the time is calcium fluoride. Calcium fluoride is one of the most simple, I'll show you the crystal structure on the next slide, is one of the most simple cubic lattice-centered crystals you can find. I chose it for 2 reasons. One is it's the most studied because it's a standard material in UV optics, especially in lithography. So in E-beam, no, not E-beam, but in optical mask writers for chip fabrication, every lenses, everything is in calcium fluoride. So this is extremely well studied and to some extent understood. And the ionic radius of calcium 2+ and the ionic radium of thorium 4+, which are both the noble gas versions of their respective atom, have almost identical ionic radius. So that means if I put thorium into this material, the crystal really doesn't deform very much because it's the sizes of the atoms or ions are almost the same. So we've been growing calcium fluoride, doping thorium 229 and other isotopes for a long time. And over a long time, we have learned how to make the crystal growing ever smaller, which is the opposite of what everybody else does, because most people in industry, they want to have a crystal like this, so they can cut it into many slices and sell a lot of lenses or mirrors or whatever you want. We want the opposite. We want to have as little as material as possible because we have a finite amount of thorium 229, and the less the volume crystal, the higher the concentration. And in the end, the laser will only illuminate a very, very small volume. Anyways, you've seen the blue trace of fluorescence in the crystal that June showed. So that's usually 0.5 millimeter of volume. And if I have such a crystal around it, it's just background and loss of material. So we reduce. And the next step we're currently working on is actually pulling fibers, single crystal fibers to even make the volume even smaller. And obviously, it would be really great if we could vary the host material easily. Unfortunately, developing a process like this takes several years, and developing it for another material takes another X years. So we can't easily switch between calcium fluoride, magnesium fluoride, maybe even thorium fluoride. We're trying that, but it's very, very cumbersome. Just to give you a feeling on how long that takes. So the way we do it is we buy a commercial calcium fluoride, the best you can get on the market. Then we mill it down to little sticks which have 3 millimeter in diameter and are about 1 centimeter long. And then we send them to a company that I will disclose in a coffee that actually is able to drill a 2 millimeter hole into a 3 millimeter single crystal. We tried and failed. Yeah, impressively. So anyway, so we drill this little hole, then we fill thorium fluoride into this little pot that has been prepared in our radiochemistry labs, which we can do because we have a nuclear reactor, and then we melt this thing to 1,640 degrees centigrade to melt, but we only melt the top half. So that means this one becomes liquid, the bottom half doesn't. And then we have a phase interface. There's an interface between a liquid and a solid, because we have half molten, half not molten crystal. And this one, by controlling the temperature very precisely, we drive this interface through the crystal with 1 millimeter per 5 hours time scale. So it takes several days to grow a crystal, although it is really very, very, very tiny. And that determines the optical quality, and a lot of properties crucially depend on how careful you can do this crystal. So there's a lot of, it's not science, it's almost alchemy. It's a little bit magic, but very painful to learn. Good, okay. So this is how it looks like. Calcium fluoride is very simple. It has calcium and fluoride, haha. And it's cubic lattice centered. So when we do doping is we kind of replace a few of the calciums by thorium, okay? And as I said, they have almost identical ionic radius. So this is, let's see if I have this, oh, look, I have an animation, great. So every now and then, and this is really sparse, every 10,000th or less calcium is replaced by thorium. The problem is that if you look at the periodic chart of elements, the calcium in an ionic crystal ionic means it wants to give away the outermost electrons and become a noble gas. Calcium has to give 2 electrons, and they're bound by the surrounding fluorines. But thorium wants to give 4 electrons. So that means if I just put it there, thorium is 2+ positive, and but the crystal doesn't want that. So the crystal will find a way to make thorium 4+. This is chemistry, and I I'm not a chemist. I have two chemists in my group that tell me thorium wants to be as if it was alive and could express its wishes. We have to discuss gender at some point, sorry. But anyways, what's going to happen is the crystal will react to make this thorium a radon-like 4+ noble gas configuration thorium in some way. And there's essentially two ways it can do this. Either it puts two additional fluorines in the spatial vicinity, or it omits a calcium in a neighboring cell. Okay, these are essentially the two ways the crystal can do this. One, we call these two interstitial fluorines, and we call this calcium vacancy. So in defect physics, this is a known thing. We're not inventing anything here. We're just reading books that are written long time before I was born, actually. So, and now it turns out that Vienna is good in modeling these kind of things on a theory basis. There's a mechanism or a toolbox called density functional theory. And when I started doing this, I traveled the world, I gave talks, and people told me, you have to use the VASP code to model this. And I wrote this down. VASP writes down like the wasp, the little animal. And I think it's great, I will do this one day. And 2 years later, I looked up what it actually means, and it stands for Vienna Ab initio simulation package. So people in my faculty that I hadn't spoken to before actually were the world experts in doing this. Okay, so that means we started modeling this, and yes, we can use a very large computer that I found out we actually have, and do these simulations. And in these simulations, we put thoriums and fluorines, and we tell the computer now move them around, calculate the wave functions, make an approximation of the Schrödinger equation, move them around, and see if it minimizes, and then it ends up with what they call stable configurations of this defect. Okay, and here they are. So this is how calcium fluoride looks. This is calcium surrounded by 8 fluorines. If I take out one calcium here, then I still end up with 8 fluorines surrounding the thorium, but they move a little bit closer. But if I put these 2 additional fluorines here, I have the thorium being surrounded by 10 fluorines. And they have essentially 2 ways of arranging them. Either they put these 2 additional fluorines between these calcium lines here, or they rearrange almost completely and come to such a virus configuration. We call this the angled configuration. There's 3, you see these slightly orange fluorines here. They have a 3-hedron, I think is the English term, configuration. So it looks like a little bit of a 3 molecule, and then there's 7 remaining fluorides, which are a little bit further out. So this is what density functional theory tells us how that should look like. And I can ask them, okay, what is the most likely one? And they say, I have to calculate the formation energy. They do that, and they turn out, okay, this one has the lowest formation energy, so we believe this is what's happening in the crystal. And just by looking at it, you see this kind of breaks the crystal symmetry, which is good, because June in his experiments or in our joint experiments, we found this anisotropy parameter, which was large. It was 0.6. It can go from 0, which means no asymmetry, to 1, which means full, I don't know, strong asymmetry. And 0.6 is already like the electric field is strongly deformed with respect to the main axis of the material. So that kind of seems to fit great. So we have some belief. Now it would be nice if we could actually experimentally determine which one is it, okay? And what would be great is if we could actually have on a microscopic level look at these fluorides and see how many are there and how far are they and how are they arranged. But obviously I don't have a microscope that can zoom on these defects. And also, as I said, these thorium defects are extremely sparse. They're not the dominating species. So the material is calcium fluoride to 99.9%, and then every now and then there's this thorium sprinkle in there. So I need a method that is really very sensitive only to the defects. And we found such a method. It's called XAPS. It's X-ray absorption fine structure spectroscopy. So what you do is you again use the spring 8 synchrotron, and you turn it to a 16 keV line, which is the inner shell L-shell electron of thorium. So that means you are energy selective. You ionize only thorium in the calcium fluoride, and the calcium and the fluoride is completely invisible to this material at these wavelengths. So the X-ray just goes through, and when it sees the thorium, it starts to ionize the thorium inner shell electrons. And this is, we didn't invent that either. This is just reading another book and using techniques that very clever people have developed over the years. And by looking at which exact energy does this L-shell ionization take place, we can learn something about the charge state of the thorium. And we find that, yes, it is indeed 4+, so that, yes, it really gives away the outermost 4 electrons. And there's something amazing happening. I'll go back here. So when this electron goes out from here, it essentially emits as a spherical wave. But then it sees the scatterers around it, and there's a back reflection, and this one is still coherent to some extent. So there's an interference effect that on top of this, sorry, that's the wrong direction. On top of this absorption signal here, there is if I increase the ionization energy, there's a backscattering resonances, and I see an interference pattern. This interference pattern, if I Fourier transform this, it tells me where the next lying outermost neighbors are and how strong they are, how many they are. Okay, and by looking at this, and I won't bother you with the details, it's a very advanced, very sophisticated method. People have been doing this for many, many decades. We can actually indeed confirm, yes, we find exactly this configuration. Here, there's 3 fluorides which are a little bit closer, and then there are 7 which are a little bit further out. And that gives us great confidence that, oh yes, we believe that if I were able to zoom into this material, I would find this to be the dominating environment. And you remember we have these 4 lines. These 4 lines correspond to one type of defect. There were two weak lines that we didn't investigate so far yet, but maybe these are other types of defects. You start looking nervous.
Oh, I have a question actually, but.
Oh, you have a question?
Yes.
Okay, then the
But
question is
also-
good, nervous is not.
No, so it seems like also, of course, June is kind of zooming in on some level with his spectroscopy of the nucleus. And so if June applied a magnetic field and looked at the quantization axes and the symmetry of the defects, could he also confirm these different models?
You would need a very, very strong external field. So it's difficult to produce external fields strong enough that mimic solid state physics. So in order of magnitude, you would need several Tesla in order to have a noticeable change, at least on the resolution we currently have. Okay, so I'll keep. Okay, so that's great. And story could be over, but there's one big problem: is the density functional theory actually gives us the electric field gradient and the anisotropy parameter, and it doesn't fit the experimental one. Not at all. Not closely, but really not at all. And we don't understand that. So the theoretical prediction is, in this case, will not tell you much, but it's minus 82 volts per angstrom squared, and we experimentally find about 110. And the minus sign is a difference in topology. It's not just, oh, if I turn around my Cartesian coordinates, it will change sign. It's more involved than, you're laughing. It's more involved than this. So it really means it's very different. Like from a topological point of view, this and this looks dramatically different. It's not just numbers being slightly off or within error bars or something. So there's something that we fundamentally don't understand. Then you could say, oh, maybe it's the other ones. Maybe we got that wrong. Maybe it's still maybe it's still this one here, right? The lobes are here. This one, which is somehow similar from a chemic's perspective, but the arrangement is slightly different. The problem with these two is they actually have no anisotropy parameter at all because they are strongly symmetric. Okay, so they don't qualify either. So there's something we understand, and that seems to make a lot of sense, but it doesn't fit the experimental data at that point, and that's worrying us a lot. And we're kind of scratching our heads. And there's one thing that could maybe resolve this, and that is that this defect is not electronically neutral at the moment when we interrogate it. It could be that if there is electronic charge sitting on the defect, maybe because the laser is pumping electrons into the conduction band and they kind of trap at the defects, that is something that is known to happen. So if this defect was intermediately charged, then that would actually fit really nicely. But that's something we have to study and we will look into, and how we will do that, I'll tell you in a few minutes. There's a question.
Yeah, so, but then you are going to get a huge internal conversion, right? Internal conversion. If you have a charge defect, you are going to get huge.
And I will keep talking, and you maybe that more sense will emerge, maybe not, let's see. But yes, you are right. If I have a charge defect, I would expect to have a decay channel that is faster than spontaneous decay. So, and that brings me to the third part of the presentation. One thing is, what can we do to check that? And June already mentioned that these splittings down here, where is it? Here it is. Okay. These splittings down here, they are nicely in the radio frequency range, and probing these is the standard technique. And again, in solid state physics, it's called nuclear quadrupole resonance spectroscopy. So about a year ago, we started buying a nuclear quadrupole spectroscopy system, and we're trying to measure these ones in the ground state. In the first excited state, we can't yet because we don't have June's laser in our lab. This is one of my basement labs. But we can scan those. If we find those in RF spectroscopy, then we're sure the DFT is just wrong, and the VASP code, you shouldn't pay for the VASP code anymore. But yeah, if we find these frequencies in the ground state, everything's good. If we don't, then maybe this charge state theory could be true, because then the energies wouldn't be here, because it's not charged when we don't have the laser. So we would have to find them somewhere else. Okay. Just to, because I'm kind of like jokingly dissing density functional theory, we did a test experiment with another nucleus, neptunium, doped into this calcium fluoride crystal, and their DFT was correct to within 5% error. So they usually know what they're doing. So something's wrong here, something's wrong, and we don't know yet. But June mentioned that, and I think this is where this is going. At some point, we will be able to know whether we are in which of these states we are by using RF spectroscopy. So eventually, we will combine these techniques of radio frequency readout and laser excitation in order to have a non-demolition measurement, maybe, if you want to translate language from quantum optics. Good. Okay. Last 2-3 slides. Is that okay still? Oh, okay. 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 So, yes, maybe charge defect. So maybe. I'll come back to this experiment where we excited the thorium nucleus through pumping into the second excited state, and then it falls down. And I have shown you this. Here it is. Okay, it's here. Okay. Well, I'll skip that. So this is the decay curve, and this is the 10 minutes free radiative decay. Now, and I said we illuminate for half an hour and then we let it decay. We can also stop the excitation and see and look at the dynamics with which the isomer is populated. And because we are in a very weak excitation regime, you would expect the same time scale. Okay, so it would actually take also 10 minutes to reach a certain equilibrium in the excitation dynamics. That's not at all what we see. The excitation is much quicker. It saturates within about a factor of 10 minutes in 1 minute, maybe, or even less, okay? And that means that during the excitation, there is a process which leads to a rapidly reduced lifetime of the nucleus. So while we are pumping up, the lifetime is shorter, so that after a short time, we reach an equilibrium between pumping up and decay, okay? And so there is an effective reduced isomer lifetime, and we have introduced what we call the quenching factor, which is just the ratio of the spontaneous decay lifetime and the excitation decay lifetime. And by playing around with the flux and the number of off-resonant X-ray photons, we can have a quenching factor of, 50. So we can, by a factor of 50, accelerate the nuclear decay. Okay, this is X-ray. So you might say, oh, maybe deep lying states are involved. There's something X-rays is dubious. It's not really quantum energies. Okay, now I tell you this thing is happening for laser excitation. Okay, so this is the excitation experiment we performed with Eckart and Pike at PTB. Also there we see an influence of the excitation timescale on the laser intensity. Okay. And again, this is the 10 minutes free decay, and we can reduce this if we go to high energies. This is still in the excitation dynamics. Turns out we can tune this effect by temperature. So if we cool this crystal, this doesn't take place. Okay, so we can either have what we call quenching in the excitation or not by changing the temperature. If that was an underlying, like deep inside X-ray energy effect, that wouldn't, temperature shouldn't matter. So somehow it's coupling to the degrees of freedom that are in the crystal. Now you say, okay, excitation dynamics, nobody really knows what's happening. Then maybe this will convince you. This is spontaneous decay. We excite the isomer, we let it decay, and then we turn on the laser again. Okay, so it's excited to a certain amount. We turn it again, we turn it on. This is this intermediate time here. See, in this time, we turn on the laser off resonant, right? We just detune it by a few tens of gigahertz in this time, and we see, oops, the isomer population is reduced. Okay, so obviously the interaction with a laser changes something in the electronic environment around the nucleus, which forces the nucleus to decay quicker. And we have done this with an off-resonant laser, the one that uses the excitation but is just slightly detuned. In the meantime, we have done this with a large variety of wavelength. So this is the wavelength that we have done in pulsed quenching. We have also done this with the CW laser, just a blue laser diode, essentially 10 milliwatt blue laser diode. That also has this effect. And again, we can annihilate or stop this effect with temperature. So we're studying this. This is work in progress. But at least I hope I managed to convince you that there is a strong coupling between the nuclear degree of freedom, in this case, the nuclear excitation, and the way we tailor the electronic environment. All right. And with this, I acknowledge the many people that have contributed, and I'm happy to take your questions.
We're running a bit behind schedule, so maybe Dylan can get, that's okay. Dylan can start getting set up. Maybe you can start disconnecting, and we can take 1 or 2 questions while we do that. There's look like there's quite a few, so I would say most of the questions we'll have to save for lunch or something. But
like so crystal structures, or I don't remember. I don't understand.
Yeah.
But
The